this series is, just say I'm gonna rediscover ellipses. Yeah, I mean, I already solved a lot of questions on ellipses, so I don't think it's going to be anything new. But yeah, let's see how it goes. Maybe I'll learn something new. Okay, so you have standard equation of ellipse, right? The definitions, everything. So standard equation of ellipse, upon b is equal to 1, 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 upon b is equal to 1. Instead of this, okay, let's just use this thing. So x squared upon capital A plus y squared upon capital B equal to 1. This thing can represent an ellipse as well as an hyperbola at the same time. So I like this one better, right? Yeah, but for an ellipse, we know these capital A, capital B has to be positive. Yeah, and then you get this thing. In fact, the thing is, if I write it in this form, then the eccentricity equation, it's not separate for ellipse and hyperbola, it's the same thing. So just capital B upon capital A equal to 1 minus e squared. So from that you can always find eccentricity. So that's nice. Right. Okay, so for ellipses, capital B are just positive, so you can replace that by a squared plus b squared, sorry, a squared and b squared, where these have some nice geometric properties. That a is the it's the distance from the center of the ellipse to one of the points where it bulges out, right? So you can say the biggest distance from the center to any point on the ellipse, right? So it's the biggest distance, and b is the smallest distance, of course. So the thing is, ellipse is basically a deformed circle. So you had a circle, we call it the auxiliary circle, with radius a, but then somebody, sorry, radius a, but then somebody just squished it. Okay, we don't want this. But then somebody just squished this, and now just have an ellipse. So these vertices are still the same, right? But now each y coordinate is shrunk down by b upon a. So this was a, now it's going to be b. Okay, right? That's nice. Wait, what is this? Okay, I think, yeah, I first checked it on smartphone, that's why this happened. So I'll just say keep both. No, just override. Well, whatever. Right. So where a is bigger than, not necessarily. Look, if a is bigger than b, then the foci are going to lie on the x-axis. If it's less than b, then the foci are going to lie on the y-axis. So for understanding purposes, so that we can deal with it right away, we can just find the foci without figuring out which is the major axis and whatnot, right? So you can always assume a bigger than b and then work out. Not necessary, even if it's like a vertical thing, so it's elongated vertically, and yeah, in that case as well, it's an ellipse. In fact, doesn't matter what the orientation is. You might have ellipses like this thing, this is still an ellipse. As long as it's a deformed circle, it's an ellipse, right? So originally the circle was something like this, and now we deformed it to get an ellipse. Anyway, equation of directrices, right? So I mean, I think already watched that video where I wrote the general parametric for any conic, right? So yeah, I mean, over there it has a good proof that why this particular property of distances being in particular ratio that defines a conic, why does that happen? So do I have to do all of this again? Whatever, let's do this thing. I know, let's just show you the thing. Why is this the directrix, right? So this point, it's negative a comma 0. Say you got any point on this, let's just call this x comma y. Or you know what, okay, let's scrap that. Since we already know it's just a squished circle, why don't we deal with the parametric form? So we can deal with a cosine theta comma b sine theta, right? So originally it was just a cosine theta comma a sine theta, that's for a circle, but then you squished it, so now it's going to be a cosine theta comma b sine theta. And now theta doesn't make any geometric sense. Before it was making some sense because it was the angle that the CT vector made with the x-axis. But now, no, it's not the thing. It's changed, right? So this is called the eccentric angle, and it's not geometrically useful, really. But anyway, it's algebraically useful at least. Okay, so now that you got this parameterization, we just want to show that this distance, which is, I mean, it's just negative a upon e, right? So distance from that, what's that going to be? A cosine theta plus a upon e, right? We want to show that this distance is, I think eccentricity times that distance, right? Yeah, yeah, eccentricity times that distance. That's equal to the distance of this point from the focus. In this case, this focus, so minus a comma 0. So for that, you just want equal to square root of, so 8 times cosine theta plus e, right? All of that squared plus b square sine square theta, right? So this thing is just, a cosine theta plus ae. Ooh, okay, ae cosine theta, sorry, ae cosine theta plus a, right? That's more like it. What about this guy? So you can just write this as, a square root of, this is going to be cosine square theta plus 2e cosine theta plus e squared. And then instead of writing b square, just write a square times 1 minus e squared, right? So this will just be, sine square minus e squared sine squared. So this becomes 1. Awesome. And then now it's going to become plus 2ec. But look, what's e squared minus e squared sine, which is e squared cosine squared. So a times 1 plus e cosine, as we expected. And yes, there's this little thing about square roots equals, the magnitude and whatnot. But hey, this thing is also actually going to be inside a mod and everything. So it's okay. It's okay. Right? And yeah, I mean, we did this for this direction, this focus, but then you can say that the same thing is going to happen over here because, I mean, just flip the x-axis, right? It's going to make sense, right? Okay. Awesome. So ellipses have this property. Then these are called vertices. I don't know why they call it. Okay, next, major axis. This thing is the complete thing. So 2a, that value is major axis. A is the semi-major axis. Minor axis, this thing, right? So this is major, this is minor, because look, this is the greatest distance, this is the shortest distance, right? Remember that, right? Principal axis. So the major and minor axis together are called principal axis. Okay, fine. Center, the point which bisects every chord of the conic through it. What? The point which bisects every chord of the conic through it. Oh, drawn through it, but oh, okay, it bisects. Right. So if you know a thing about linear transformations, the thing is, so originally you got this circle, the auxiliary circle. This, so draw any chord, right? Any random chord. You know that this center, it should technically be a diameter, but whatever. Just one chord through the central point. So yeah, the diameter. So we know that this central point is going to bisect it, right? Yeah, and then, so I don't know, call this thing as x comma y and this thing as negative x comma negative y, whatever. And then after the linear transformation, this thing is still 0 comma 0, but now this thing is going to be, x comma b upon a y, and then this is going to be negative x comma negative b upon a y. So it's still the midpoint, right? So this vector and this vector, they are still opposites, it's still the midpoint. Cool. There's no need for this kind of definition. Well, whatever. I mean, isn't it very intuitive to call it the center? Why do you have to define it like that? Whatever. Next, diameter. A chord of the conic which passes through the center is called a diameter. Okay, understandable. Focal chord, right? So a chord which passes through the focus is called a focal chord. For parabola, this makes much more sense. But then for an ellipse, I don't know. Double ordinate. A chord perpendicular to the major axis is called a double ordinate. Oh, so for example, this is a double ordinate. It's a latus rectum, yes. But okay, this might as well be a double ordinate. So this thing is also double ordinate. Fine. Latus rectum. The focal chord perpendicular to the major axis is called. Okay. Oh yeah, so the length of the latus rectum. 2b square upon a minus x square upon major axis, which is like, so 2a times 1 minus e squared. Okay, it's like 2e times the distance from the focus to the corresponding directrix. Understandable. From the focus to the right. Okay, no big deal, it's understandable. But no need for doing us. I mean, 2b square upon a is good enough. You don't need all of this. Just 2b. Okay, why is that the case? So x squared upon a squared plus y squared upon b squared equal to 1, we said. So at x is equal to ae, what will your y be? That's gonna give us this half of double ordinate. So an ordinate, whatever. Find that out. Put ae in there, so you're gonna get a squared, e squared is cancelled, so y squared is equal to b squared times, is that right? Wait, ae, that's what we had to do, right? So to get the thing, it's gonna be 1 minus e squared, but that has e squared. Okay, whatever, so 1 minus e squared. That's unexpected. I didn't think it would be like that. So okay, but 2b squared upon a, that's what we look for. That should have been the thing. Why did this happen all of a sudden? It's got to be right. I mean, the focal point through that you want the ordinate, so it has to be ae. But then x squared upon e squared just turns out to be e squared. Doesn't make any sense. Wait, and then y squared upon b squared is equal to, yeah, I mean, okay, fine. So that's 1 minus e squared. 1 minus e squared is like, okay, it's equal to, b power. Oh, yeah, it is the thing. This was like squared, so hard to recognize, but whatever. B power 4 upon a squared, and that just means y is equal to the positive value of y. That's going to be b squared upon a. But we want twice of that because this is just ordinate. We want the double ordinate. So 2b squared upon a. Whatever, next property. Right, so let us assume it's just 2b squared upon a. Sum of the focal distances of any point on the ellipse is equal to the measure axis, to its measure axis. Oh yeah, okay, so this thing, right? This is actually a really nice property. Let me show you why it's the case. So you got this ellipse, not like this font. Ellipse like this. So you got these as a directrix. I don't know. Just say these are directrices. What do you know? So any point on this ellipse, right? It has the distance of, let's just say this is S1 and this thing S2. So this distance will just be, e times this distance, right? And then this distance is just e times this distance, right? We already proved that. But that means their combination is just e times this complete distance. And what's that complete distance? It's going to be 2a upon e, because this thing is at minus a upon e, right? This thing is at a upon e, so 2a upon e, and that is e. So the sum is going to be 2a. Cool, right? Yeah. And from there you can clearly see why this relation, b squared equal to a squared as well as e squared, why does that hold, right? It's pretty obvious, because if this happens, then this this length, so let's just draw it out. You don't want all of this. So remember, till now we actually not have used what b, I mean, for this particular property of this, the distances being in this particular ratio, we have not used what b is, right? Yeah, doesn't matter what b actually is, it's still okay. And in fact, no, we have used b. We have also used it. So maybe let's just say that till then we defined b to be, a times square root of 1 minus e squared. So it doesn't have its own identity, but in fact it doesn't have its own identity in any case. But yeah, we define it like that. Okay. But now we want to define it differently, so we want to define it using that squishification property. So this is like squished by b upon I, something like that, right? So for that, you have to realize the fact that this distance, this distance is going to be equal to a as well, right? So let's just call, I don't know, let's see, this is b dash. So after the linear transformation, so making your y into b dash upon a times y, after that linear transformation, if this thing is b dash and this thing is just, this whole length is ae, right? But we know that the how do I call this thing? The ellipse. So not this ellipse. Let's just say it's some other ellipse with the same foci as this thing, right? That ellipse has this property of, you know, yeah, doing that thing. And then B for that guy is just, 1 minus e squared. But then you know that uh, for the topmost point of that ellipse, so not this ellipse. Uh, okay, this is getting crazy, right? So topmost point of that ellipse. So if this distance was B, right, this would have been equal to A and everything. Okay, let's just skip this. Let's just say that, yeah, I mean, it is all so interconnected that you can't just go from one place to another. You have to first of all divide it like that. There's another way. Ah, okay, whatever. So you just have to deal with that. Fine. But hey, still a good thing because you can draw some geometrical significance from that. That the sum is just 2a, so you can think about this length s1bs. That's going to be 2a, but then by symmetry you know that s1b must be a. But then you can complete a right angle and then say a squared e squared plus b squared is equal to a squared, and from that you can get eccentricity. Although that's not how it should have gone. It's in fact you first define b squared to be this thing. Yeah, so then it's like really obvious, but still, yeah, even without actually defining b like that, just I mean defining the whole conic using that property that the distance from directrix is, and then that times a is the distance from the focus, you would get the same curve, but then you would not know what b is. So then you can figure out what b is through this little geometric thing. Okay, yeah, but now we have already defined it, right? So we went the other way around. I was trying to go to other I was trying to go to the the more geometric, but no, it is got to be algebraic. Next. Okay, this is all the properties, right? And what about these nodes? Oh yeah, okay, yes. So if this is the equation and nothing is mentioned, through this resume is bigger than b. Oh, I mean, it's not very good that you have to do this, but whatever. Position of point with respect to an ellipse. Ah, right, of course. So, position of a point with respect to a circle, right? Just do the linear transformation and then say, yeah, it's pretty much the same kind of equation. So if x squared upon e squared plus y squared upon b squared is less than 1, it's inside the ellipse. If it's bigger than 1, it's outside. If it's equal to, then it's on the ellipse. Auxiliary circle, eccentric angle, right? So, of course, we already explained this, that an ellipse is just a squished circle, and that's why, yeah, right? I mean, from this equation itself, x squared upon a squared plus y squared, you know that b cosine theta comma b sin theta is gonna work, right? Sorry, a cosine theta comma b sin theta is gonna work, and then from that property itself, you can say it's the squished circle. So the circle that got squished is the auxiliary circle. Yeah, whatever. You don't need all this formal definition. Parametric. Okay, no, we already know this. Line and ellipse. But the equation to the chord of the ellipse joining two points with eccentric angle alpha and beta is given by this. Oh, interesting. Right, so equation of chord of the ellipse joining these 2 points, alpha and beta. So what's the slope? The slope between 2 points with eccentric angles alpha and beta, what's that going to be? It's going to be b times of the subtraction of the sine values, which is like 2 times sine of alpha minus beta upon 2, cosine of alpha plus beta upon 2, and then upon same kind of stuff, just a. Yeah, we want the tangent, right? No, okay, chord, whatever. The thing is, we want this. Okay, chord. This will be a times of 2 cosine of alpha minus. Yeah, it's negative. No, it's supposed to be in that case sine of the reverse difference, which is beta minus alpha upon 2, and then sine of the sum, which is alpha plus beta upon 2. So yeah, this just becomes negative after this cancellation. Just get like negative b upon a cot alpha plus beta upon 2, and then from, yeah, I mean like y So just say delta y upon delta x is equal to this thing. That just means, a sine of, or let's just not do that. Let's write it in a different way, right? Let's write like this thing. Y upon b sine of alpha plus beta upon 2 plus x upon, actually delta y, right? X upon delta x upon a cosine of alpha plus beta upon 2, that's equal to 0, right? That's the thing. But then from that you can see the delta of this whole thing is equal to 0, right? So what does this delta x really mean? It just means, yeah, like the change in the y value between any 2 points on the line, not necessarily the 2 points between which you want the chord to be. No, any 2 points on the line, right? So then from this equation you can say this has to be equal to some kind of constant, k whatever. But then yeah, like we know that one of these points is this, cosine alpha, if a cosine alpha or b sine alpha, right? That's gonna satisfy this equation as well because it lies on that chord. So just put that in there and you'll get the thing, right? Yeah, sure. So that just means, x upon a cosine of alpha plus beta upon 2 plus y upon b sine of alpha plus beta upon 2 is equal to, just put that point in there to get the value of k right away. That will be, so a cosine alpha, right? Sine alpha times cosine of alpha plus beta upon 2, and then plus sine alpha sine of alpha plus beta upon 2. Does that ring a bell? Of course, it's gonna ring a bell. Alpha minus alpha plus beta upon 2, which is like cosine of alpha minus beta upon 2, right? That's why this is the equation. So nice, I guess, right? And then from here, if alpha and beta both become the same thing, it's gonna be a tangent, right? Which just gives us x upon a cosine. Let's call this as theta, right? So alpha and beta both approach theta. So theta right there, and y upon b sine theta is equal to this. Just becomes 0. So cosine of 0 is just 1. That's the tangent, right? And yeah, like from that you can get this thing that the tangent in the slope form can be written as y equal to mx plus or minus square root of a square m squared plus b squared. Now there's the other way to do this as well, which is using this equation, right? So using that you can get this for both hyperbola as well as the ellipse, right? So that's the other way to get this thing done, of course. Yeah, right. So using this thing you can get that, right? Okay, let's think about it. How would we want to do that? Let's say x naught y naught is a point that sits on this thing, right? Then the tangent would just be x naught upon a plus y naught upon. Look, I already made a video on why this works and everything. Okay, fine. You guys are beginners. I shouldn't be doing that. I shouldn't tell you all of this, crazy stuff. Let's just go the basic way. Just gonna take a different differential of this thing, right? So like 2x upon a plus 2y, and then slope upon b is equal to 0, right? So x and y both are, I should say x naught y naught, because then it will make more sense that these are actually constants. These are just so x naught y naught is just a point that lies on this ellipse, that is, it follows this equation. And then from here you can say the slope is just, okay, where it go, yeah, like minus x naught upon a upon y naught upon b, right? Cool. So right, now that you know the slope, yeah, so the thing is y equal to mx plus c. That is, suppose that's the tangent, right? That's the tangent to this curve. Then of course x naught y naught, which is the point of contact, right? We are assuming that that's where the tangent originates from. So if that's the point of contact, this should satisfy this equation. From that you can say y naught is equal to mx naught plus c, but then we already know what m is, so you can figure out what c is. C is just y naught minus mx naught, which is like plus oh, we already know what m is. So yeah, like b upon a, so that goes on the top, this comes down. Then you got x naught upon y naught, and that times, well, x naught, right? Oh, okay, you know what, scrap that. What we'll do is we'll just say x naught upon a times x naught, like squared upon a, upon y naught upon b, and then cross multiply, you just get x naught squared upon a plus y naught squared upon b. But guess what? That's just 1. So 1 upon y naught upon b, right? So yeah, from this we can get, c being this thing, and m is that. And then the thing that they want to do is find out what c is in terms of m. That is, basically they're saying like c squared is equal to a square m square plus b square, right? So squaring both of these, you get like c squared is equal to b squared upon y naught squared, and then m squared is just b squared upon a squared, and then y naught, where did that go? Right, y naught squared upon x naught squared, right? And then they're saying, okay, we just want, over here they're using small a square, actually it's supposed to be capital A. So capital AM squared and then plus b. What will that be? It's going to be b squared y naught squared upon a x naught squared and then plus b, right? So you can just take b common. It's going to be b times of b y naught squared upon a x naught squared plus 1, which is like, so b times of b y naught squared plus a x naught squared, that thing upon, is that going correct or not? Oh, it's got y naught in the denominator. Oh, okay. So that's why it went wrong. Supposed to be x naught squared upon y naught squared. Right. Okay, so then, pretty much the same stuff, except that just have b x naught squared plus a y naught squared upon a y naught squared. Now we already know what this thing is, right? What bx naught squared plus a y naught squared is. That's going to be ab, right? Because it stands on ellipse. So this will just be, b squared upon y naught squared. But what's that? C squared. So that's why c squared equal to a m squared plus b squared. This works for everything, for hyperbola, for ellipse, right? Any conic that can be represented like this, which is only the hyperbola and ellipse. But you get the idea. It works every time. Yeah. Okay, cool. So this same thing is also going to carry on in hyperbola as well. So you might as well just use this equation derive this equation in the most general form, so that you can use that without worrying in the hyperbola as well, right? So this is awesome. Okay, what else? We already did that this thing is a tangent and whatever. Yeah, no big deal. Oh, we did that this is a tangent. Did we do it? Yeah, that was obvious because alpha, beta both approaching theta, then the chord at theta, which is actually more like the chord at theta plus, theta and theta plus something very small, which is a tangent at theta basically. Okay, the eccentric angle of point of contact of two parallel tangents differ by pi. What? Eccentric angle of point of contact of two parallel tangents. Of course. So yeah, this is correct, right? So two parallel tangents, yeah, that is the thing is, you could go figure out how slopes change in a linear transformation and then do the thing, and then you will see that yes, it's the same. But you could also do it more algebraic, and both ways are correct. I'm not going to do it myself because why waste time on that? It's very trivial to do that, right? Conversely, if the difference between the eccentric angles of 2 points is p, then the tangents at these points are parallel. What is p? I think it's supposed to be pi, right? So yeah, both are correct. So the second one is in fact easier to prove. The first one requires some kind of thinking, but whatever. Next, point of intersection of tangents at the point alpha and beta is this thing. Intersection of tangents. Oh yeah, okay. So just yet another point that right. It's like a cosine of alpha. Oh, this is like not good. It's not good, huh? Okay. Think about it. What's it like? So say that point is x and y. So x comma y. What do we know? It's gonna do these things. X upon a cosine of alpha plus y upon b sine of beta is equal to 1, and at the same time it's also going to do this thing, x upon a cosine of, sorry, it's cosine of alpha right there, cosine of beta plus y upon b sine of beta is equal to 1. You know what I'm thinking? It's like x and then you got cosine alpha. Okay, maybe that's not the best way to be thinking about it. Yeah, I was really thinking about it, as vectors and stuff, but let's not do that. Maybe just want the point of intersection, right? Yeah, you could just solve this, right? I mean, yeah, the solving it is the best thing to do. But then once again, who is ever going to use this equation, right? No, I will not. I will never use this. I've never used this till now, so no need for it in the future as well. So yeah, you have this formula, not really useful. The equation of normal at x1 y1 is this thing. Oh, so this is actually important, right? So the thing is that the tangent equation. Okay, I think it's understandable. I mean, you already got the fact that the tangent is of the form, a cosine theta upon, sorry, x cosine theta upon a plus y sine theta upon b is equal to 1, and then this is of course of the form x. Okay, let's just say x naught. So x naught is the point with ascending angle theta, that upon a squared plus y naught upon b squared, right? Both of these equations are identical, so you can always write this like that. No big deal about it. Then the question is, what is the normal, right? So to get the normal, you just got to reverse the slope and make it negative. So to do that, I'll just say x a squared upon x naught, and then I'll put a negative to reverse, so to make it opposite, right? So negative, and then this makes this reciprocate, yeah. Then minus y b squared upon y naught, and now it's not going to be 1. It's going to be some kind of constant which we don't know, but we do know that the point x naught comma y x naught comma y naught is where the normal is going to pass through, right? Because that's where the normal originates from. So just put that in there and you'll get the value of k. Easy as that, right? Yeah. So putting x naught comma y naught, just get a squared as b squared as the value of k. Awesome. So that's nice. Equation of the normal at the point. Once again, pretty much the same stuff. Just put x naught y naught as a cosine theta, b sine theta, and you'll get this thing. Equation of a normal. So for hyperbola, you get plus over there, so it's more, I don't know, beautiful or something. But even for ellipse, it's just as much important to do this thing. Equation of normal in terms of its slope is, okay, no, we don't want that. I mean, you could do this, but why? Why do you want to do that, right? Directors, look at this. Who is going to remember all of this? Not me, certainly. Locus of point of intersection of the tangents which meet at right angle is called a director circle. Yeah, right. The director circle for ellipse is just x squared plus y squared equal to a squared plus b squared. So I don't think it's that bad to prove that it's gonna be like that, right? Can't be that bad. But still, let's just do this. So we want all the points which basically like have 90 degree between the tangents from them, right? Yeah. So how do we do that? Hey, look, we already had a formula for this for the point, right, of intersection of the tangents, right? This thing. So we can use that directly, and all we have to do is just have the tangents being perpendicular to each other. So for that to happen, so we know what the tangents are like, yes, and what's the slope. So for a tangent, the slope in terms of eccentric angle, that's going to be, so cosine theta upon a upon negative sine theta upon a, right? That's the slope, which is a negative cot theta times b upon a, right? So if two tangents are perpendicular, right? What should happen? So just multiply this together. So b squared upon a squared cot alpha cot beta, like that thing has to be equal to, that has to be equal to -1, right? So that means tan alpha tan beta is equal to negative. So this is yeah, negative b square upon a square, of course. And what we want is cosine of alpha plus beta upon 2, and then upon cosine of alpha minus beta upon, and then similarly for sine and all that stuff. So this 1 upon cosine of alpha minus beta upon 2, take that out actually. Yeah, right. And then this has to think. Okay, okay. This is weird. Not looking good. Not looking good. You could just multiply by, just say cosine of alpha plus beta on both of these. Right? I don't. Okay, that's why I don't like formulae like these, because sometimes they're just not useful, right? Maybe this was not a good idea to use. So what would be the actual good idea then? So you want perpendicular tangents, and of course the locus of point where these tangents will be perpendicular. How do we get that? Get that? I don't know. There must be the only way to do this is using algebra, but I don't want to be doing that. So it's right. This is like so badly written. I don't want it like that. Just solve the thing. X. This is so not good. X cosine alpha upon a plus y sine alpha upon b is equal to 1, and then x cosine beta upon a plus y sine beta upon b is equal to 1 as well. We know that so we know that tan alpha times tan beta is equal to negative b square upon a square. And we know that both of these equations satisfied by that point. So now what can we do with it? What I'm thinking is, just isolate this and then try to do that. Okay, that's one thing that we can do. Anything else? Other ideas about this? It's equal to negative. It's equal to 1, right? You can always take the difference, right? That's one thing. But we want like cosine alpha cosine beta and sine alpha sine beta, not just that. Yeah, of course. Oh, why don't you multiply by cosine beta right there, and then sine. Ooh, no, that's not going to work, because when we subtract, okay, that's not what you will get. You will get something else. So you don't want to do that, of course, right? That's probably not a good thing to do. You could just accept that that's the thing. Like a squared plus b squared is the radius. Yeah. Okay, I should prove this, right? I should prove this. That's how it's supposed to be. So you got cosine of alpha cosine of beta upon b squared, I think, right? And plus sine alpha sine beta upon a squared is equal to 1. That's, wait, what? Oh, so cosine alpha cosine, sorry, wait. Yeah, that's right. So cosine beta upon b and plus, like, okay, what I'm thinking is, right, that's gonna work. So cosine beta, you just want upon b squared. Wait, that's different. So you gotta have a upon b squared, right? So a upon b squared cosine beta, comma, similarly you just gotta have upon a. So it's like, is that correct? Guess it is. It really is, huh? Wow. Nice. That's nice. Oh no, it's supposed to be a. Oh, it's supposed to be sine, like cosine over there. Fine, it's supposed to be a squared and b squared. Now it's even better, because in that case, you can just say, okay, if this is replaced by cosine beta upon a and this thing is replaced by sine beta upon a, then sine beta upon b, then this will work, right? So okay, that point is a candidate for this thing. And then similarly this will also work. What if this is replaced by, oh hey, what about a cosine alpha comma b sine alpha? That also works, right? Because cosine square alpha plus b sine square, of course, I mean that's gonna work. So that works. Okay, what else? Oh, the average of like cosine alpha plus cosine beta upon let's not do a. Okay, and we already had this, so not the best. Yeah, the only way is actually to figure out what x and y are and then use this thing to get the thing done. I don't like that. Just don't like that. Yeah, I wish there was something else. But other than all this algebra, there's no other way, right? I hate this. Of course, just hate this. Yes, but really, is there no other way? I mean, okay, why am I so adamant on proving this like silly identity? Why? This is such a small thing. We can just accept it, right? Without doing all the algebra. Still, I really think there might be a better way to do this than just algebra, right? But what better way? What better way? X, Y, these are like, uh, whatever X and Y are, both of these like do this. Okay, fine. What will satisfy that kind of solution? Okay, cool. So plus Y squared, that's what you want, right? Oh, wait a second. Look at the solution. Okay, what about this? So think about the equation, x x call this thing x naught y naught, right? That's the point that will do it, of course. Or about, let's just say x naught and oh, why am I using just use the code of contact and stuff, and that will work, right? Yeah, okay, we don't have that accessory right now because we are at beginner level, so we can't do it right away. So let's do it some other way. So I'm thinking, okay, x naught upon a times x plus y naught upon b times y equal to 1. Like this thing, right, this thing is satisfied by cosine alpha upon a and cosine beta upon, cosine alpha upon a, sine alpha upon b, and cosine beta upon a and sine beta upon b, right? So both of them satisfy, sorry, no, cosine alpha and sine beta and cosine beta and sine alpha, right? So both of those satisfy this equation, at least you can say that, right? Okay, understandable. Or okay, maybe you can do this thing or something like that. And at the same time, they'll satisfy another, right? Yet another equation, which is this thing. Okay, cool. How is that even yet? Yeah, how is that even useful? I don't know. Like that guy somehow. Okay, whatever. Just move on. Just move on. There's no other way. You just have to do algebra to do this thing. So y equal to mx plus or minus square root of am squared plus b, and y equal to negative 1 upon mx plus or minus square root of a upon m squared plus b, wherever these guys intersect, right? So whenever these intersect, you start like 0 is equal to m squared minus 1 upon fraction x plus 1 upon m times x, whatever this thing is, which is like plus minus square root of am squared plus b, and then the other stuff, which like the constants don't really matter, do they? No, they don't. This the thing is, if this is plus, right, you have to keep it plus. If it's minus, you have to keep it minus, right? So yeah, okay, then just have to subtract this out, right? That's all you did. Now what you get? So this is gonna have 1 upon, right, like m plus minus 1 upon m. That's what you're gonna get. And then you can do the same kind of thing. So upper times something and lower times something, and then subtract. Yeah. So I will just say upper times 1, lower times m squared. And then, okay, let's not subtract, let's add. In that case, you will have a different version of this difference, like minus plus. And then just have this thing, you multiply by m, right? Ooh, we had to multiply by m squared, like m over there. Ah, of course. Right? Yeah. There's no m over here, it's supposed to be 1, sorry. And then when you add, you just get m squared plus 1 times y is equal to plus minus square root of a squared m squared plus b squared, and that times 1 minus plus, because yeah, we didn't subtract, we added, right? And then it times m, of course. That should do it. Yes. So this will be m plus minus 1 upon m, and yeah, right, that works out. So from this we just get like, okay, this just gives us m squared plus 1 times x is equal to, oh, and this m cancels in any case, right, and then this comes over here or whatever. Slightly different one expected, right? This was negative, so it's going to be minus something, and this is like minus 1. Okay, yeah, this is actually telling us that no, it can't be like identical. No, that's not correct. Not correct. It's got to be something different over here, right? Oh, okay, that's that m over there. Did we not use? We got m squared. We got this upon m over here, and then we did it just like that, subtracted it out. Oh, that's bm squared. Oh, okay. So this is am squared plus b squared, and that's bm. So okay, that's why this changed. Right. So this is not the thing. This is not how it's got to be going. Yeah, it's like m. Okay, this is gonna be very different in that case. So still it's plus minus am squared plus b, and then minus square root of a plus bm squared. And this thing subtraction, of course, no, addition, right? M squared plus 1 times y is equal to, so, and now I'm just losing count of how this plus is supposed to be minus plus, right? Yeah, I'm just losing count of how it was supposed to be minus plus plus minus, I don't know. Plus minus square root of a squared, just am squared plus b, then minus plus, no, now it's going to be plus minus sort of a plus bm squared, right? Yeah, right. And then this can be moved over here, so just get m squared. Oh, and by the way, it's supposed to be actually 1 upon m squared. Right. So for this guy particularly, you just get m over here. For this guy, you're gonna get upon m, so it's like this thing upon m. Wait, what? Okay, whatever. And then for this, this m will cancel, just get m over here. So m squared plus 1 times x is equal to minus plus square root of a squared am squared plus b, and then minus plus, right? No, okay, now that's plus minus square root of a plus bm squared. Yeah, of course. Yeah, sure. And then what is square these and add these up, right? So you're gonna get m squared plus 1 squared, and then x squared plus y squared is equal to, so squaring is adding up, right? And oh, that's m over, this is supposed to be m over here as well. Yeah. On the other one, so this had a okay, over here, I guess, right? Exactly. So when you square and add, of course, oh, and this is supposed to have bm squared right there. When you square and add, so that product thing, that's opposite sign in both, like that will cancel out itself, right? And then you just got this guy squared, this plus m squared times all that, so it's like a squared m squared plus b, and okay, this thing squared, so there's no a over there, a plus bm squared, right? Then plus, so this thing complete square is like am squared plus bm power 4 plus, okay, this thing complete square is like am power 4 plus bm squared. Now if I add these up, what do I get? So just a, then plus b, and then plus, so for m squared just have like a plus b. Oh, and also where the other thing is, so you got m squared over here, m squared also 2 times of a plus b, and then plus m power 4 times a plus b, right? So you just got to do this thing, a plus b common, 1 plus 2m squared plus m power 4, which is, guess what, just 1 plus m squared. And then I know this is like not satisfying. I thought there would be something better, but that's what it is. So square, sorry, and this cancels, so that's my x squared plus y squared to a plus b. This works for both hyperbola and ellipse. So in this particular case, capital H is a square, capital B is b square. So it's like a square plus b square. For hyperbola, it's going to be a square minus b square. Anyway, so now that's done. So, right. Wait, what was I doing? Directrix locus. Then diameter. The locus of middle point of the system of parallel chords with slope m of an ellipse is a straight line passing through the center of the ellipse called its diameter, and the equation of right. Okay, this is of course from the linear transformation. So first, so I have to do it. I have to show you how the slopes change. Right. So initially, let's just say you had a line with slope m. So m was delta y upon delta x, right? And then let's just say these are the 2 points between which you are taking the slope. And then after the transformations, just call this thing like x1, y1. This is x2, y2. After the transformation, what happened is that this got squished out, right? All of the space, 2D space got squished out. This got x1 b upon a y1, and then x2 b upon a y2. That would be the new coordinates of this thing, right? So the same point got moved, basically. And now the slope would just be, right? The slope would just be, so b upon a delta y. So this delta y refers to the delta y that we're using previously, right? Okay, these are the same thing. Then upon delta x. Sorry, this is not supposed to be happening. So you can say, okay, the new slope is the original slope, but that times b upon a. So think about it. If there were two lines which, sorry, okay, if there are two lines which make make 90 degrees each other, that is m1 times m2 is -1, and then you do this linear transformation, what's going to happen to their slopes? They're going to be b upon a times the slope of the first guy, b upon a times the slope of the second guy. And yeah, now what's the product of these slopes? m1 times m2, that is negative b squared upon a, right? Sorry, a squared. Yeah, so m1 m2 is equal to negative b squared upon a squared. So now what do we know is, so if you had a circle, and then whatever chord you have, you don't care about what the chord is like, and then you know that its midpoint, if you join that to the center, this line that you get, that's perpendicular to this thing, right? And then from that you want to apply a linear transformation on this thing, and what will happen is that this slope will change. This slope will call this slope as m1. Okay, now this thing as m1, and this thing as m2. So both of these slopes will change, and then what will happen? This have m1 dash m2 dash, that will now be negative b squared upon a squared. Cool. So yeah, that's cool. But the thing is, this point is still the midpoint, right? So this vector is still equal to that vector even after this linear transformation. Even if it was like a rotation transformation, it would still be the midpoint, right? That's the thing. So now the line connecting, so for an ellipse, right? For an ellipse, the line connecting the midpoint of the chord to the circle, if that has slope m2 dash and this has slope m1 dash, then we'll just not use that dash everywhere. Now we're talking about this ellipse only, not this. Okay, so if this has slope m1, this has slope m2, then m1 times m2 has to be negative b squared upon a squared, right? So yeah, this is nice. Okay, next. Wait, how many are there? A lot of properties are. Okay, diameter circle is done, diameter is done. Anything else? Important highlights referring from ellipse x squared upon a squared plus y squared upon b squared equal to 1. If p is any point on the ellipse with s and s dash as its focus, then lsp plus, come on, we already know that, right? The product of the lengths of perpendicular segments from foci, oh yeah, that's important. This is equal to b squared. And the feet of perpendicular lie on the auxiliary circle, right? The tangents at these, so right, I mean, this is, let's just say it involves a lot more calculation, and yeah, right, a lot more calculation. Should I even do this? No, I mean, usually they do this in lectures, right? This is just supposed to be a quick walkthrough not a full-fledged lecture. So yeah, this property is, let's just say it's very non-intuitive that why should this happen, right? Okay. Yeah. What do I do? How do I write? Okay, maybe like geometrically, maybe that will work. So you got this ellipse, the foci are, I don't know, over here or something, right? This completing is our A. Okay. Then what we are saying is you got this tangent. You want to drop a perpendicular from, let's just say, one of this, okay, this focus to that. This is going to be perpendicular, and what you're seeing is that this will lie in the auxiliary circle, that is the distance from this to that, that will be A, right? That's the thing, that's what you're saying. So how do we get this distance, right? So we know this thing is going to be AE. That's 90 degree right there. Okay, cool. You got this tangent, and okay, that distance is like not nice. You definitely don't want to be doing that. What about just inverse the linear transformation, right? That would be good, I think. Yeah, yeah, that would, in fact, I think that would be good. So just reversing the linear transformation. Nah, probably not. I don't think that's the best way. Okay, so just gonna do some kind of geometry to get the thing done. Yeah. First of all, we have to prove that both of these actually lie on the auxiliary circle. So for that, we have to prove this is actually equal to A. Okay, how do we do that? How do we do this thing? It's tangent to this. Okay. It's not angle chasing or something. No, that just won't work. We can of course figure out what this distance is. Well, this distance is slightly more complicated, but now that we know what the slope is actually doable. Not that hard, I think. So this, yeah, like algebra, you still have to use some algebra. Ah, okay. What's the variable thing? The Of course this is the slope, right? Yeah, is that's variable. Sure. So slope is variable. Okay, if the slope is, so for this tangent, right? The slope is m. The magnitude of that is m or something. Then you know the tan of this angle is going to be m, right? We want the cosine of this angle, which is, so like 1 upon secant is like 1 upon square root of 1 plus m squared. And that times AE is what this distance will be. The square of that is going to be a squared e squared upon 1 plus m squared. So that's the square of this thing, and then you just want, this distance squared, and for that you can of course use the formula to go from 0 comma 0 to this thing. Yeah. So what's the line? Y is equal to mx plus minus square root of 1 plus, sorry, a squared plus m squared, right? So from 0 comma 0 to this, what's the thing? And then square of that, of course, like that's gonna be a squared m squared plus, I didn't write it like that, oh god, a squared m squared plus b squared, that's what we think. Plus b squared, so you want to do the square, of course, upon m squared plus 1, right? So yeah, leg 1 squared plus leg 2 squared, which is, so m squared plus 1 common, it's got a e squared plus b squared, but remember what's that? That's going to be equal to a squared. So just a squared, and then you can take it out, so 1 plus m squared. And this still works, yeah, but it's not so beautiful. So yes, this is on the auxiliary circle. And then the other thing was proving that the product of these two, that's like, that is in fact equal to b squared. So I mean, do the same thing over here as well. Hang on, what's happening to this guy? Right. So once again, this. So you can figure out what this length is going to be, right? And we already know what this length is. Yeah. So that length is just square root of a square m square plus b square upon square root of m square plus 1. Now you want that length minus, call this in d, so minus d, and then the same length, so call this in l, I don't know, and then l plus d. Actually l minus d refers to this length, not this length, but you get the idea, right? Yeah, and this is the same length over there. Okay, so then it's just going to be this guy squared, which is just a squared m squared plus b squared upon m squared plus 1 minus d squared, right? So minus this guy squared, which is of course like tan of this angle, which is the slope itself, times a. Oh, sorry, the sine of that angle times, right? So for sine theta, you just gotta do m times of that. Yeah, and that thing squared, of course. Just want a squared m squared upon m squared plus 1. That should do it. And that's going to be, so upon m squared plus 1, and then look, a squared m squared, but look, a squared minus a squared e squared squared. That's going to be equal to b squared, right? So when you collect these two terms, it's just going to be b squared m squared, and then got plus b squared, it's going to be just b squared, of course, as expected. So the distances multiplied, these distances multiplied, it's going to be b squared, right? I don't know why are they just proving properties, but if I just leave it like that, I feel like okay, I just fast forward the whole thing and it's not correct. Anyway, that's done. If the normal at any point P on the list, I mean, it's crazy. They have not yet presented a reflective property, which is pretty big deal actually. If the normal at any point P on the ellipse with center C meets the major at minor axis at G and G respectively, if C, F, if, okay, you know what? Yeah, okay. I did read all of these properties when I was like preparing for ellipses, right? So the major test basically, but let's just say there's just too many of these to remember, right? Yeah, just too many of these to remember. What are you gonna do? Remember all of them? Seriously? I don't think that's doable. Okay. And then what else you have? So this is about what normal point. So normal at any point P on the ellipse with center C meets the major matrix at G and G, and CF is the perpendicular on this normal, right? Then you have some stuff going on. Okay, fine. Yeah, definitely not going to do it. Then you got locus of midpoint of GG is another ellipse having the same eccentricity as that of the original ellipse. I'm pretty sure they're going to ask questions on this thing, so we just have to prove it. Otherwise, what is this? Just a problem for what is this? From what? Looming? I don't know what this thing is. Okay, so should we do H3? What is this? Why are these H1? Oh, highlights, and that's why. Fine. What is this? The portion of the tangent to an ellipse between the point of contact and the directrix subtends a right angle at the cusp. Oh yeah, this is actually something that I have been asked a lot of times. So, right, that subtends a right angle at the corresponding focus, right? So portion of tangent to the ellipse between the point of contact and the directrix. Yeah, got this ellipse, got this tangent, this is our point of contact. Directrix might be somewhere over here or something. Yeah. Oh, okay, this is a different what I was right. So the other property. Okay, so this is a not that property. I was thinking it was, but no. The other property was different. But hey, whatever. This also looks cool. What we're seeing is that at this focus, right? This is going to subtend a perpendicular, right? Okay, that's what they are trying to say, I think, right? So just have to prove this. Okay, cool. How do we do that though? This is supposed to be perpendicular. Since it was like the directrix and the focus, the focal directrix property, maybe that's what we should be using, I think. So this length, call it as L, then this length has to be L times E, and this length is, oh, okay, this is the tangent. That's also important. This is the tangent, right? That is very important, I think. What's tangent at that point? Hey, isn't that, oh, you could just use the other focus and then use the reflective property and do some stuff with that, right? So what I'm thinking is just draw this complete line, right? So you got this other focus, it's supposed to be like, maybe not the best way to do it, actually. It's a tangent, that's the problem. If it was any random, thing, it would be okay, but if it's a tangent, that's kind of complicated actually, right? So drawing this line, and you know, like these two angles have to be the same. Okay, the tangent might be intersecting this over here as well. Okay, cool. And of course, you also have this being perpendicular. Yeah. Okay, cool. So this is pretty obvious that both of these have to be similar, right? Because they make the same. Yeah. Okay. Yes. Both of these have to be similar because with this tangent they're making like the same angle. Okay. You got 90 degree over here, and then from that itself you can see these are like similar. Okay, no problem. Now, if this length is L, this length is going to be L times E. The thing is, it's like a tangent. This being a tangent is going to make everything complicated. Hmm. This length is, it's like A times of, no, this is just too much. You definitely don't want to be doing it geometrically because this tangent is just, right. So you're saying this is supposed to be 90 degree. Hmm. I don't like this. I don't really like this, you know. Anyway, so if this point is, yeah, just scrap geometry. We're gonna do coordinate geometry now. X naught, Y naught is the point. Then what is this going to be? So the tangent is x naught upon a squared plus y naught upon b squared equal to 1. So the point might be a upon e comma y. Just put that in there. It's supposed to be x naught upon a e plus y naught upon b squared equal to 1. So our y coordinate is just going to be, let's solve for that. It's 1 minus x naught upon, you know, you can just write this as cosine theta upon e or something. So yeah, and then y as well, you can just write this as like sine theta upon b and stuff. So y would just be b upon sine times 1 minus cosine upon e or something like that, right? Okay. This is awful. Why are we doing this? Something better than that? I don't know. 90 degree over here. Why? Well, whatever. So you got this thing y equal to p upon s, you got 1 minus c upon e. That is this guy's y coordinate. This guy's y coordinate we already know, and then this is supposed to be perpendicular. This slope, you can do that thing, of course. What else can you do? This has to be perpendicular, right? There's another way. You just have to figure out these two slopes and then multiply them. You're gonna get -1. What other choice do we even have? We also have that other parameterization. We can use that thing. But you don't know about that, or maybe you do, but then it's not related to the thing. Why should we do that? Just really want to use that other parameterization. Let's just see if that's gonna work. So, a e power I theta upon 1 minus e cosine theta. Okay, this e is different. It's supposed to be capital E something like that, right? So this parameterization is, you know, when you got the focus as your origin, and then this is whatever conic you have, and then you got this as the directrix, right? You can use this parameterization to get the xy coordinates. Yeah, of course. The real part is just x coordinate. The imaginary part is the y coordinate. Yeah, and then theta is just this angle actually. Okay, cool. And then you are saying that the tangent, like it intersects over here, and then this angle is supposed to be 90 degrees, right? Basically, that's what you're saying, right? Okay, okay, interesting. What is this angle going to be in that case? I mean, you can of course figure out what that angle is supposed to be, right? And the fact that this is like 90 degree, it's really weird, you know. The fact that it intersects over there, and that gives us the 90 degree. Why? Why that? Why not something else? Oh, and by the way, this capitalized. Yeah, okay, no, just do the algebra. Don't use this because it's already something that I don't want to use. This is what you should use. So you got y. This point now we know is just, you know, a upon e comma b upon sine theta times 1 minus sine theta upon e. And then this point we know as well. So it's just a cosine theta comma b sine theta, and then you gotta multiply these slopes together. So for this guy, the slope will just be b upon s times 1 minus c upon e for and then upon, so a upon e minus this, which is like just a. Okay, that's at least, sorry, a. That's nice because this thing is constant. And then this times this slope. So from here to here, it's going to be b sine theta upon, what is this going to be? A cosine theta minus a e or something? Yeah, ac minus a e. And what we are saying is that these are, yeah, like perpendicular. Huh. Interesting. Isn't it? Of course, of course. Okay, so now what? Like b squared upon a squared, this cancels. 1 minus c upon e upon 1 upon e minus e times c minus e. Yes. Right. Guess that's how it's supposed to be, huh? Fine. This should be negative 1. So like e minus c upon e, that's one thing. This e goes down, it can become 1 minus e squared. Oh, I think this is making sense now because, yeah, so like this will cancel, it's going to become negative 1, and then a squared times 1 minus e squared is just b squared. So this is actually just 1. This whole thing is just 1. So negative 1 is the answer, but not a very nice method. I wish there was something else I could do. Oh god, these properties is going to keep on going because there's so many of these. It's weird. I've never actually used all of these properties. I don't even know half of them. And it still works out. Like, I don't know. Ellipse is not that hard. Yeah. What is this? Circles on any focal list. Right. Should I just keep on? What's the time now? 5:49. Yeah, I'll just keep on going. I'm gonna prove all of these properties, I think. Now that I've started, yeah, just gonna do it. Okay, cool. So, wait, what was I doing once again? Yeah, this property I did, h2. Let's go for h3 in fact. So if the normal at point P on the ellipse with center C meets the measured and minor axis in G and G respectively. So what's the normal? We already got the equation for that, but just write it down once again. So x times, oh, that a is gone, right? Okay, you have to flip that. Right, this is the normal. We already know this, right? And I mean, I just proved this. Of course, you know this. Yes. You are saying it. Where did that go? Right, it means the major and minor, that's the x-axis and the y-axis in capital G and small g. So capital G is going to be, so whenever y is 0, x just becomes, you know, cosine upon a times all of this. This is like a squared e squared, isn't it? Yeah. So x would just become c a e comma 0, and then so for small g is going to be like that 0, and then negative s a squared e squared upon b. Yeah. Okay, so right, that's capital G and G, and CF be the perpendicular upon this normal. Ooh, that's interesting. Maybe we draw out a figure or something. So you got this as normal. It's going to intersect with these points. This thing is going to be capital G, this one is small g, and then you are saying draw a perpendicular to this normal. This is a what? F? Right, where is it? Center C, okay. CF be perpendicular, right? And then what? And then you are saying then P F, so this is point P, okay. PF times PG is equal to B squared. Okay, so this times that. Look, PF, that's already a hard thing to do because this is you have to figure out the perpendicular. Seriously, though, that's not, I'm not gonna do that. Okay, that's not something I want to do. The multiplication is like B squared. Just distance is all of the time, right? You know what I'm thinking? I could just deform this back to a circle and then, right, maybe that's going to be a better thing to do. or something pf times pg. Why that? Wait, okay, I think I'm getting to some. Look, it looks a lot like what you get in the PowerPoint. Yeah, I think I remember a derivation of the. I mean, the same four properties like that. So I'm just gonna draw a circle through it. I mean, I can, sure. That's perpendicular, right? This midpoint is the center of this circle, and then PF, sorry, at that times PG, that's gonna be this power of point of this circle, right? So of this point with respect to that circle, you're saying that's equal to B squared. That's just the, the S value of this P with respect to this circle whenever it hits G. Well, we know what G is. I mean, this guy. So what's the circle going to be, right? Yeah, that's the thing. We know this point is just going to be A comma E, which is also the radius, in fact, right? Oh, sorry, C times A. Okay, CAE upon 2. Right, that's this point, and the radius is also CAE upon 2, and then you just want D squared minus R squared. That's gonna be this thing, G times F. Sorry, PG times BF, right? Yeah. So yeah, D squared from this cut from this point, huh? That's already complicated. Fine. Or you could just do that thing. Yeah. So the thing like x minus CAE. Right. So instead of having this d squared plus r squared, we figure out the equation and then do d squared plus r squared directly without even actually calculating it. And this times, of course, x, because that's one thing that lies on that, right? That's one of the diametrical points. And then both have no y coordinate, right? 0. That's why the thing. So x squared plus y squared minus x times of CAE is equal to 0. So this is also actually representing d squared minus r squared. So for this point P, just take x common. Okay, we know what x is, a cosine theta, and then a cosine theta minus a cosine theta times E, and then plus y squared is like b sine theta squared, of course. That has to be equal to what? Okay, that's equal to of course pf times pg. What is that going to be? It's like a squared times, so c squared, and then you got 1 minus c squared, right? Not square, is it? Is it a square or not? That was oh, there is a square, sorry, I missed that. Okay, right, and then plus b squared sine squared. Look, this thing is just b squared, so that's why b squared times c squared plus sine squared, and that's why just b squared is this thing, right? P. I wish there were like geometrical properties that I could just use to get this thing, but no, you have to do it algebraically most of the time. Okay, then pf times pg. So once again, the same thing, like this is the circle I will draw, and of course these 2 points are the one that we use. So both have 0 x coordinates, just x squared, and then plus, so y, so for this just y, and then y minus this guy's y coordinates, that's like plus s a squared e squared upon b, right? This thing is also representing d squared minus r squared. So for p, it will be like a squared c squared plus so y just becomes, what's y? B times sine theta, and then this just becomes b times sine theta plus, like, okay, that just constant. Okay, sine theta is there, and then got a squared e squared upon b, not squared, sorry, which is like this a squared c squared plus take that sine theta out, like b sine squared theta, then you got b squared plus a squared is just a squared, and that thing upon b, cool, this cancels out, and yeah, so this thing is just going to be equal to a squared plus c squared plus s squared is like 1. Okay, this property done as well. Nice. Oh, it's raining. Okay, third, pg times pg. Okay, these two are the same. Oh, okay, you mean like this times that. Hey, this is also 90-degree right there, so you can draw this circle. That's equal to sp times s dash p. Oh, come on. When am I going to use this? Because there's like 4 things right there. Why would I even use that? But this looks somewhat like I don't know. Something like PowerPoint, yeah, but different. This circle, right? Like that. Huh. That's equal to SP and then S dash. Why? SP S dash. This is like eccentricity square times the distance from the directrices, right? I mean, okay, I guess we can prove this using, the same thing. Just do G and G and then draw a circle through that. Yeah, not into it. Not going to do it. Right. Once again, something weird like why? CG times. Oh, this is not that hard because this is actually a constant. Sorry, I should have said this is not that useless because it's a constant. Here it's not a constant, it's changing throughout. So yeah, not really into doing this. This looks good. So CG and then this thing. Right, we already got these lengths actually. Let's multiply them out. It's going to be cosine sine. Is that for real? CS squared, but this is not a constant. Why is that? Oh, what's this T? What's T over here? Capital G. And then, oh, I think you mean the tangent, right? So wherever the tangent is, right. Yeah, that must be T, of course. What else could T be? So T is whenever the tangent hits this. Oh, look. Well, that's equal to CS squared, huh? Slope is just, both of them have the same slope. CG then. This also actually has a circle through it. So this is the circle that we were talking about, right? Right, circle through that. Through T, capital G as well as T, right? So we just want the distance from this point to, okay, something like that. The power point of this guy. Then S dash. Okay, CS squared, right? Huh. CS squared. Why? Why is that the case? Yes, just some point over there. Something else? Something else that you can do? Your CP and then some point at. No, it's not gonna happen. Don't do that. Ah, horrible. Or you could just, figure out what these actually are and get the thing done, right? That's, yeah, I think that's what we should do. No geometry, just algebra. What's T going to be? So the tangent is like x sine upon a plus y sine upon b is equal to 1. So whenever x is 0, just your y, oh sorry, whenever y is 0, x just becomes a upon c. So t is a upon c comma 0. So of course, this times that constant, right? What's that? A squared e squared, which is of course c squared. So yes, okay, but not helpful all that much. Locus of midpoint of capital G small g is another ellipse having the same eccentricity as that of the original ellipse. Right, so yeah, I mean, you can see like this is just C, and look, the thing is, it was like a square minus b square, which is some kind of constant, and then you had upon a, and then this is also like that. You can write this as a upon b, and then that times b over here, and then this is going to be same stuff, same kind of constants, but this times of a. So yes, it's also just a deformed ellipse, and with a and b as the dimensions. Right. Just this is switched and something. Yeah. Okay. Of course. And yes, this also is in fact centered around the center, the origin. That is. Same eccentricity of it, of course. But SS dash are the foci of the ellipse. Of that ellipse. Oh, interesting. But in this is like the y. Oh, the midpoint. Still, the y coordinate has the bigger value. What happened? What happened? Okay, fine. What do you mean? SS dash as the foci of the ellipse? No, that's not correct. definitely not correct. You can see that, right? Yeah. How would that be correct? I don't know. T is the point where tangent at P meets the major axis. Oh, okay. So that you wait. So when you said SS dash, you actually meant uh oh, okay. Of the original ellipse. That's what you meant, not this new ellipse, right? This fifth is just another property like these four, not right. This lower line is not for the fifth property only. It's for all five of these property. Okay, the tangent and normal at a point P on the ellipse bisect the external and internal angles. Well, of course, reflection property. Each focus to the foot of perpendicular from other focus. Oh, hey, okay. Now I remember what. Look. Yeah, of course. So using the reflective property, you could just easily prove the director circle property. Right, but that's kind of cheating, we know, because the reflective property is like, okay, fine. So suppose you do get perpendicular tangent somehow, right? I don't know, it's not, maybe that's a right. Okay, so you just get perpendicular tangents somehow, we don't know how. And then these are the foci, it's gonna draw perpendiculars to these tangents. Yeah, right. And then just want like the x squared plus y squared thing for that. That is, yeah, that's what our aim was, of course. We know like both of these points, they lie on the auxiliary circle and everything. Yeah. Okay, this looks like it's from, it's not supposed to be looking like that. You know, this should be more random. This is better, I think. And this also, just move it a little. Yeah, this is better. Okay, cool. Of course. And sorry, what were we once again doing? Right, okay, these 4 points lie on the auxiliary circle, right? Yeah, that was the thing, of course. And we had to prove that this point lies on the circle with radius a squared plus b squared. Yeah. So to get that distance from, you know, the center, how would we do that? Wait, was this the property that they used to prove the director circle property or something else? I don't remember this. And oh god, I don't remember the thing at all. Huh? Whatever, you know, like, okay, this length. Okay, these both are on the auxiliary circle. Fine. That's perpendicular right there as well. You know, okay, the multiplication of these two. Hey, wait, if all of these points are like on the auxiliary circle, like for this guy, x squared plus y squared is just, yeah, okay, that's a squared. Similarly for that as well, x squared plus y squared is a squared. This is as well doing that. Okay, no, I don't remember what they used to do. Okay, the multiplication of these is supposed to be b or something. Wow, I really don't remember anything now. This is not good. Not good. Yeah. Wait, okay, what are they saying? Hence, we can use a straight line joining each focus to the foot of perpendicular from the other focus. Each focus to the foot of perpendicular from the other focus upon tangent at any point P. Okay, this is some other property actually. So tangent at point P, this is the foot of perpendicular from one of the focus, from the other focus, and then you are saying the lines joining each focus to the foot of perpendicular from the other focus upon the tangent, that is this point, this line, of course. Okay. What about this line? Meet on the normal PG and bisects it where G is the point. Sorry, G is the point where normals. Okay, this is something weird now. Huh? Straight lines on each focus. Oh, okay. So this straight line as well as this straight line. So you're saying okay, these meet at this point, and okay, so this is on the normal. G is the point where normal at P meets the x-axis. So it should be over here or something. Huh. Meet on the, wait, what? Normal PG and bisects. Oh, okay. So you are saying, right. So this thing is G. You are saying these two lengths are the same. Oh, okay. That's what you're saying. Fine. Okay. That's understandable. So what do we do? Reflective property, of course. Uh-huh. Right. What's that name? I don't know. So these are supposed to be bisecting that. That's crazy. Why? Why would these be bisecting that? And how do I use the reflective property now? Because this point is like, okay, this is taken by that. This is crazy. Yeah, this is like so random. Why would you want to do that? It's perpendicular right there. Ah, why? These two mate, oh, so these are concurrent, right? These three things are concurrent. Okay. Why is that the case? But what if I just prove that this line bisects it, then okay, then it would be correct to say that this also bisects that, right? So if I prove both of them bisect it, and you're done, because then it's gonna be concurrent in any case, right? So just have to prove that these are, bisecting this. Okay. Interesting. How do we do that? This is quite random actually because it's perpendicular. Then oh wait, okay, these two are 90 degrees, and oh okay, wait a second, these are already parallel, we know that, right? Of course, these are parallel. These are, it's like a trapezium or whatever. I was thinking maybe these are on some kind of circle. No, they're not. Okay, these 2 points are on the auxiliary circle. Understandable. Other than that, do you know anything? Right, okay, these being on the auxiliary circle, but that's not passing through the focus. No. Just passing through the vertex and everything. So that's not correct to do. Right? You can't do it like that. Why these foci? What's so important about them? Right? This circle, nah, won't work. Supposed to be bisecting each other. This is very random. Why should that happen? Why should it bisect? And how is the reflective property useful in it? How is that giving us anything? Okay, these two are going to be the same angles, right? That's all it's saying, that these are the same angles. Huh. Right, so these are the same angles. Product we know. So why is that bisecting? They shouldn't. There's no need for it to be doing that. Wait, okay, maybe it's like the midpoint thing or something. Wait. If I just extend this. Okay, look, this is bisecting that. We know that for sure. And oh, it's parallel to Thales theorem, of course. Right. Which means it's the same ratio. Oh god. Yeah, it's gonna bisect that. And from that we can prove that this is also gonna bisect. Right, so similarly, right, just draw this out. Yeah, sure. Similarity triangles. Look, the thing is, this is just the median of this bigger triangle, but then this is like parallel to the base, so it's also getting bisected by this. Of course, of course. Okay, nice property, but how useful is that? I don't know. Next, the portion of tangent to an ellipse between the point of contact and the directrix. Oh yeah, this thing. We did this. We did this. Okay. The circle on any focal distance as diameter. Focal distance as diameter. We like this. That touches the auxiliary circle. Touches the auxiliary circle. Focal distance, right? Not the, not like this whole thing, not a focal chord, just the focal distance. And that has a diameter, touches the auxiliary circle. Why should that be the case? Okay, let's draw it bigger so that okay. So that's our circle, and you are seeing this is touching the auxiliary circle. Ah, crazy. So if I just draw the tangent, right? So this is a diameter. You know that, like the perpendicular from this guy is gonna lie over there, but then this actually lies on the auxiliary circle. So according to you, this is the point where it's gonna touch the auxiliary circle. It cuts it. I don't know. I don't care about that. It touches it. That's interesting. Right. It's pretty interesting. Why is that gonna happen? Because that's implying something other than that. That is basically saying, okay, if I just reverse the, okay, no, that's gonna make this an ellipse. I was thinking maybe I could calculate radius of curvature of things using this. No, that's not right. Okay, so it's going to be intersecting at this point. I get that, but why is that going to touch over there? We are saying this distance, which is half of this, right? So half of this distance. That's the center, of course, and the auxiliary circle has this center, right? So you are saying because these are like touching, what should happen is that these 3 points, they must be collinear at the same time. This length must be equal to r. Okay, that's sorry, equal to auxiliary, yeah, e, sorry, that's already equal to a, we know that. But these being collinear, why is that the case? It's the midpoint, huh? Interesting. Right, it's the midpoint of this focal distance. That is the center of this thing. Okay, right. Right. These are I don't know. Doesn't look obvious to me. The midpoint of these two, what's that going to be? So like a cosine theta plus a e upon 2, and then a sine theta upon 2. And this point is, that's not nice. Right, this point is hard to calculate. Anything, so any other test of collinearity, right? Anything else? So if just the distance between these 2 points is actually the radius of this whole guy, so like the focal distance, half of the focal distance minus this thing. Okay, no, that's not nice. This complete, oh right, so this is equal to a, and this thing is just this distance, right? Yeah, right. Oh wait, oh look, actually this triangle, huh? And then this is like, okay, you can't use this right away because the thing is this is not yet a line. We don't know if it's a line or not. So that's not nice. It's definitely not what you should be doing. The only test that we can use is figure out this radius and also this length and add them up, and if it somehow adds up to being a, and then yeah, that would be it. That would be saying that the auxiliary circle is being touched at this point. Cool. So for that, first of all, you need to figure out what this length is. Interesting. Midpoint right there. Okay, how do you figure out that length now? This length is actually not that hard, right? Because we just want, you know, the distance between this and that, the focal distance that is, which, yeah, not that hard. So like from x equal to a upon e, that's the distance, right? So a upon e minus this guy's x coordinate, which is just a cosine theta, right? That's that distance, right? That's this r. And now that plus this distance, so this is a slightly more complicated, right? So plus, you know, basically this distance you can say, yeah, which is, so this guy, okay, like square root of, take, oh, we got b over here, sorry, not a. Take that 1 upon 2 out. Now square this, a squared times c squared plus e squared, and then plus b squared, which I'm going to write like a squared times 1 minus e squared, and that times of s squared. So a upon 2 square root of c squared plus, oh, this thing is, sorry, c plus e squared, right? So c squared plus e squared plus 2ce, and then plus s squared minus s squared c, so x squared e squared, right? So a upon 2, hey, didn't we do it already somewhere? Yeah, I think we did. I don't know. Okay, then this just becomes, it's like, this is 1. Then e squared, okay, that's gonna be 2ce, and then plus, that is e squared, right? So like plus e squared c squared, which is a upon 2 times 1 plus ec or something. Hey, isn't that right? Oh yeah, it is. It really is. We already got this expression somewhere. I don't remember what this actually is, but it just, ah, that's this distance, right? Right. Okay, something like that. Whatever. This is what you got, right? Okay. So that's going to be a upon 2 plus a e c upon something like that, right? This is that distance. Okay, that's not, it doesn't space. Wait, what? But there's no AE right there. It's just that, nothing else. Ah, interesting. This distance, of course, to figure out, we just did this much, right? And that, oh, eccentricity times that. Okay, so it's supposed to be a minus aec, and then this plus, wait, just a little more. Right, you want to take half of that, because the thing is, what we actually found out, yeah, actually contains a half. Right, this distance is what we found out, right? What we had to find out, and what we actually found out is this distance, which is like eccentricity times this x coordinate distance, right? So half of that is what we are looking for. Now that's going to be a upon 2 plus aec upon 2. So the sum, sorry, minus, it's supposed to minus right there. So the sum, that's going to be a, just like that, and that means this is actually equal to a. Okay, cool. So that's nice. Yeah. Right. This is actually going to touch the auxiliary circle, although it doesn't feel like this is going to happen. But hey, you never know. Like this, okay, it's not touching it, as you can see. But that's because my drawing is bad. It's going to touch it. That's what's supposed to happen. Okay. So that's nice. Okay, we did which property now? Yeah, we did at 6. Now at 7, perpendicular from center upon all chords which join the end of perpendicular diameters of an ellipse. What? From center upon all chords. So from center to a chord, perpendicular. Sorry. Which join the ends of any perpendicular diameters of the ellipse. Perpendicular diameter of the ellipse. That's a diameter. You want two perpendicular diameters. chord joining the ends of the perpendicular from that, right? Uh, that is a constant, right? This length is a constant. That's what we're saying. Huh. Nice. Okay. You want to prove that now? How do we do that? Okay. Think about it. How do we do that? Isn't that okay? This is like 90 degree right there, and this is also 90 degree. Not useful. Hmm. Similarity of triangles or something. Yeah. All angle is theta. Uh, oh god, it's like perpendiculars. Huh? Okay, perpendicular diameters. Hmm. But in this distance is like constant. I don't get why that should be constant. Oh, that's this is also going to be no, not necessarily. This is not theta. Yeah, might be something else, right? Right. Okay, these are of constant length. Interesting. Why is that the case? Perpendicular diameters. Hmm. And then from that, you want to drop a perpendicular to this chord. Why? Why is that going to happen? You can do angle chasing and trigonometry and things like that. Okay. Uh, what exactly is it that we know about this? Do we know the length of the diameters? No, no, we don't. Like given this angle, so let's call this angle as alpha. Can you actually figure out what the length of the diameter must be? Well, I don't know. Doesn't look like it. Okay, so eccentric angle. Given this eccentric angle, maybe you can actually figure out the length of the diameter, right? Yeah, that's not nice though. I mean, you don't get a nice length, right? And then in the end, you have to do this kind of geometry. So, so all this length is L1. If you do get something nice, I don't know, it's L1, L2. So L1 tan theta is what this length is, and then sorry, L1 sine theta. And this is a L2 sine theta. Sorry, L2 sine of this angle. So L1 sine theta, call this thing as H, I don't know, is equal to H. L2 cosine theta is equal to H. So from that you can say 1 is equal to H squared upon L1 squared plus H squared upon L2 squared. Maybe, just maybe, actually turns out to be something nice. Yeah, you gotta figure that out. So H squared is equal to, right, so first of all, got to deal with it. What's 1 upon L1 squared plus 1 upon L2 squared, right? So any length squared, right? This length squared. So if this has eccentric angle is alpha, I don't know, called as alpha, then the length would just be, you know, cosine squared a squared plus b squared sine squared. Yes, which is okay. And you want 1 upon that thing. Okay, cool. Right. And then for something, so this is like in alpha, of course. And this guy, so this angle is got this angle is 90 degrees, right? So the slope, of course, is got m1 times m2 is equal to negative b squared upon a. And then going from here to here, what actually is the slope? It's going to be b upon a times, no, it's not, it's supposed to be negative 1, sorry, and negative b squared upon a squared. That's what it's supposed to be, but hey, you can take it. M1 m2 is equal to negative 1 actually. And what's m1? So a cosine theta, b sin theta, going from 0 to 0 comma 0 to that is going to be b upon a tan theta. So we'll just got tan theta 1 tan alpha, and tan beta, that's equal to, so this is going to be b squared upon, okay, minus a squared upon b squared. That should be doing it. Yeah. Okay, cool. So this is the thing, right? Now what? What to think about it? And then like 1 upon it's just this quantity. Similarly, you will have 1 upon cosine squared, you know, beta a squared plus sine squared beta, and then b squared. And yeah, now what? What after this thing? right? You could of course try breaking this into bits. That's not going to be helpful. Ah, okay, you can write a square as b square upon 1 minus. No, no, wait. Yeah, okay, b square upon 1 minus e square. That's one thing. Or I can write b square as a square so minus e square. I think that's better. And this whole thing is like 1 upon a square, and then you got 1 upon cosine squared alpha plus sine squared alpha uh, minus e squared sine squared alpha, right? So basically 1 upon a square, and then you got 1 upon 1 minus e squared sine squared alpha. And similarly, you got other guys, so minus e squared cosine, sine squared beta, right? But how does this become this, right? That's the question. Wow, I have no idea. But this is the thing, you want 1 upon h squared. So h must be a constant. That's what we want to prove. Then this must happen, but now what? You are stuck. Because cosine alpha spawns. Yeah, like that's what we have, sine alpha, sine beta, cosine beta. Not helpful, not helpful. B square cosine alpha cosine beta. No, no. Not helpful. Think about it. You want to get an expression, right? You would like a constant expression or something. How do you get that? You gotta cross multiply and everything. So 1 upon a square, and then this will be e square times sine square alpha minus sine square beta. Yes, you can do that, but then in the end, how do we use this? How do we use this property? Because without using this property, we are not going to land anywhere, right? Yeah. Must be something. Must be something that we can do about this. It must be a constant, but why is this not working? Okay, what I'm thinking is like we just put that right there. So b square sine square alpha plus sine square whatever, and then just square that, right? So from that you will get at least something about this, right? Maybe that's a good idea. You could try it, right? Of course. Yes, we should try it out. But okay, that's gonna give us sine square alpha times that square beta. We want not the multiplication, we want just addition or something like that. Fine, just keep on going. We'll see what happens. We got 1 minus e square sine square alpha plus sine square beta plus e power 4 sine square alpha sine square beta, right? Now, yeah, I mean, this should turn out to be something of the form sine square alpha minus sine square beta. How? I think the only way is actually to figure out this, right? This is going to equal to negative 1 upon 1 minus e squared. Then that goes over here. It's sine alpha sine beta times 1 minus e squared is equal to negative cosine alpha cosine beta. From here, you just want to square this so that you can get this thing at least, right? Okay. So you got sine square alpha sine square beta, and then this guy square is like 1 minus 2 e square plus e power 4 whatever. That is equal to cosine square. This is like 1 minus sine square. That's 1 minus. Yeah, so alpha, sorry. This is going to be 1 minus sine squared alpha minus sine squared beta plus sine squared alpha sine squared beta, right? Okay. So from here, okay, this is going to cancel out, I think. Sure. Nice. What does this tell us? E square common got e power 2 minus 1 and then sine square. What? No, that's not what I want. No, that's not what I want. I want sine square alpha minus sine square. Oh, both of these like plus. Sorry about that. It's not subtraction. So, right, don't do it like that. It's supposed to be 2 minus e square sine square alpha minus e square sine square beta. Hopefully, this will turn out to be. Hey, outlook. That's okay. Okay, okay, wait a second. Sine square alpha plus sine square beta, isn't that just, 1 minus, right? So sine square alpha sine square beta times e power 4 minus 2e square. So if I put that everywhere, maybe I'll get something nice. So it's got 2 minus e square times that, guys. So minus e square plus e square sine square alpha sine square beta times. So, oh, you got an e square already. So like just e power 4, and then this should be e square minus 2. So basically like e square minus 2 times negative 1 plus e square sine squared alpha sine squared beta. What about this guy? Just put that right there. This is awful. Why am I doing this? Just putting that over here. Oh god. Yeah, okay, so 1 minus e squared, and then what's again plus e squared times all of this. So plus e squared, and it's never ending. So like all of this, which is just, I mean, we figured that out. It's supposed to be just that much, right? So e power 4 sine square alpha sine square beta, and you already have this other e power 4. Why? Okay, e power 4 sine square alpha sine square beta, and then you just have e square minus 2, right? And then yeah, right, that's how it's supposed to be. And then plus e power 4 sine square, right? So what's that going to do? It's gonna make this minus 1. Yeah, it's like e square minus 1 times negative 1 plus sine square alpha, sorry, e square, e power 4. Yeah, right, that's also supposed to be e power 4, because yeah, e power 4 sine square alpha sine square beta. So yes, it does cancel out, but you can see what we had to go through to actually get this. So it's e square minus 2 upon e square minus 1 in this case, right? So 1 upon e square, sorry, 1 upon a square, and then e square minus 2 upon e square minus 1. That's equal to 1 upon h square. So h is just equal to a square root of e square minus, we could say, just say 1 minus e square upon 2 minus e square. Yeah, that's gonna work. Sure. Okay, so that's what h is. That property done as well. Right. Last property, the tangent at the point P of a standard ellipse meets the axis in T and T, and CY is the perpendicular on it from the center. Then tangent at the point P of a standard ellipse meets the axis in okay, in capital T and T. Right. And CY is the perpendicular on it from the ellipse. Oh, come on. No, I'm not going to do this. Right. It's just like this question. You have to figure out circles and then the power of point. Oh, come on. So let's be squared. I hate this. Least value of capital T times small t. Oh no, it's like t. That's the distance, right? That's this distance. Okay. That's a square. Sorry, that's a plus b. Huh. And then tt dot py. Py is perpendicular. Oh, so py is this thing. Oh, that's like, okay, that's the power of point of p with respect to the, so if it's gonna meet at t somewhere over here, I don't know. And then this is a, so point c, it's gonna drop up and go from there, it's like y or whatever. Yeah, so capital T, right, it's gonna be bisecting over here, capital T, small t, and then py. Wait, what? Uh, okay, no, not helping, not helping. Capital T small t times EY. Now even that is not working. Huh? This was like capital T small t. It would have worked. Now it's not. It's not gonna work. We can definitely think of it like okay, PT and then so P capital T and then P small t. So you want to break it like that and then add up, right? So it's like the power of point of this P point with respect to this circle and then that complete bigger circle, right? Oh yeah, not going to do this because just unnecessary torture, right? So this will have to wait for tomorrow. In fact, not even tomorrow. It's gonna be day after tomorrow. So till then, bye. See you guys in the next video.